Hello, my name is Zang, and I'm a student at Clements High School in Sugar Land, Texas. Today, I'll be presenting my project, Automated Particle Detection in AFM Images of Environmental Films using two novel algorithms. So, what are environmental films? Environmental films are thin layers of microscopic particles that deposit on surfaces outdoors over time. They can be formed through a plethora of processes and can be commonly found on solar panels, buildings, etc. Although they may seem innocuous as they are microscopic particles, these environmental films may reduce solar energy efficiency of photovoltaic cells and also accelerate a degradation of architecture. Unfortunately, the mechanisms behind environmental film growth are remain poorly understood, and this is where AFM comes in. AFM provides high-resolution topographical data with atomic scale precision, and the identification of particles from AFM data is thus incredibly important. There are plenty of existing approaches to AFM particle identification, but they all have significant drawbacks. Manual identification is time-consuming, while watershed and texture-based segmentation struggle on mixed particle populations. Additionally, machine learning methods, which are accurate, have limited accessibility and reproducibility in many applications. Thus, there exists a gap between highly sophisticated but resource-intensive methods and simple, widely used techniques that remain prone to bias and error. Importantly, none of the aforementioned approaches have been tailored to environmental films. The best software that we have are Gwydion and IYRC and are available for general use. We will focus on IYRC in this work. IYRC is particularly common in surface science research, however, it has notable limitations. IYRC requires manual adjustment of masking and flattening particles for each image, and it also merges large adjacent particles into a single object. Additionally, IYRC produces false detections, such as edge particles, which may be removed automatically, and zero-area particles, which must be manually removed. Here's a visualization of IYRC's limitations. In figures 1a and 2a, we can see that particles are all bounded with large particles merged together. However, these large particles are excluded in 1b and 2b because they are edge particles, leaving them out of the analysis. So in this study, we seek to bridge the gap that we mentioned earlier. We present two fully automated algorithms to solve the issue. So how do we acquire the AFM data? We use an atomic force microscope and span several dozen samples from outdoor environmental films collected from distinct regions of the United States, different substrates, and different time scales. These images had 10 by 10 micrometer dimensions, and we used two channels, height trace and amplitude trace. Height trace images were used for algorithmic particle analysis, while amplitude trace images were used for manual particle identification. I used a white top hat transform as one of my morphological transforms in my algorithms. The white top hat transform is especially effective in isolating particles in images with rough backgrounds. It's abbreviated WTH. In addition, it enhances small bright features and suppresses large-scale background variations, as seen in this figure. Additionally, we also have adaptive Gaussian thresholding, abbreviated AGT. This compares pixels to a local threshold rather than a single global value. Additionally, it accounts for spatially varying backgrounds, ensuring that particle loss is minimized. Finally, we have a contour tracing algorithm which geometrically bounds particles as visualized in the next slide. We also automatically remove zero area particles, which improves on IGRPRO's inability to do so. And so the red boundaries in this case are the visualization of the particle boundaries of the particles identified in my algorithms. And here are the definitions of my algorithms. We have algorithm A and algorithm B, where the difference is the white top hat transform in algorithm B. This sacrifices runtime, but as we will see later, it increases the accuracy of algorithm B. To validate our algorithms, we used manual particle identification. We selected 16 images from a diverse set of AFM images of environmental films, and we labeled 2,014 particles in total. This is the scheme of the manual particle identification. Each AFM image is 10 by 10 micrometers, and we use 4 2 by 2 micrometer regions per image. Finally, to evaluate our algorithms, we classified each particle as true positives, or false negatives based on the algorithm results compared to the manual ground truth. In addition, we measured the root mean square roughness, a measure of roughness that was obtained from IGRPro for each image. We next computed performance metrics of precision, recall, and F1 scores shown on the screen. In addition, the zero area rate was defined as the ratio of the zero area particles detected to the total particles detected by the algorithm. We then ran a RM ANOVA and then post-hoc pairwise comparisons to compare a performance across algorithm A, algorithm B, and IGRPro. Finally, here is a summary of the results. Overall, algorithms A and B both outperformed IGRPro, with algorithm A demonstrating faster processing and algorithm B achieving higher detection accuracy. Here is the visualization of the results. We can see that algorithm B in figure 7b outperforms algorithm A in 7a, which significantly outperforms IGRPro in 7c. So for our runtime, algorithm A was more than twice as fast as algorithm B and 25 times faster than IGRPro, representing a 96.6% reduction in runtime. This makes algorithm A extremely productive in real-time applications. Here is the graph of the runtime versus RMS roughness of the images. We can see that lower RMS roughness and higher RMS roughness increase the runtime of IGRPro, but the runtimes of algorithm A and B stay very, very low and constant. Next, we have precision. The precision of IGRPro was significantly outperformed by both algorithm A and algorithm B. Here's the box and whisker chart for that. We can see that also IGRPro had a smaller consistency as the standard deviation was larger. Next was recall. Though no significant differences in recall was found, we found that algorithm B slightly performed higher than algorithm A and IGRPro in this case. We can see that again, IGRPro has lower consistency within its sample measurements. Next, we also have F1 score, which is a combination of the precision and recall scores. Algorithm B scored an F1 score of 0.66, which is 43.5% higher than IGRPro's 0.46, which demonstrated its balanced precision and recall. Additionally, algorithm A already provided meaningful improvements over IGRPro as well. By balancing both precision and recall, higher F1 scores lead to greater confidence in the experimental conclusions. Here's the box chart for the F1 score. Notably, algorithm B has the highest F1 score and also great consistency. And finally, we have the zero area rate. On average, 34% of IGRPro's detections were particles with zero area that had to be manually removed, while for algorithm A and B, this number was 0% because we had already deleted all of zero area particles automatically. And finally, as mentioned before, algorithms A and B exhibited lower standard deviations than IGRPro across all the measured metrics, indicating more stable and reproducible performance. Algorithm A is optimal for speed, and algorithm B is optimal for accuracy. In addition, the two automated algorithms provide generalizable results as they were trained on datasets that were from very diverse environmental films. Algorithms A and B also substantially reduce the manual workload, reducing the runtime by upwards of 2 orders of magnitude, and also being fully automated, reduce the manual parameter selection that IGRPro needs. Finally, future actions that we could take this include synthetic image validation and, more importantly, the extraction of quantitative particle properties. Currently, we have the identification of particle properties down, but the extraction of the quantitative particle properties would be extremely important as well. And next, we also could have approaches such as dual threshold methods that could separate the smaller and larger particles to make sure neither population is worsened. To conclude, this work presented two automated algorithms that improved upon the existing IGRPro for AFM particle detection in images of environmental films. Algorithms A and B increase the accuracy, efficiency, and consistency relative to IGRPro, and also may accelerate research on environmental films in the future. They may even expand the use of AFM in particle analysis, where precise and efficient segmentation is critical. Here is the acknowledgments and code availability. I would like to thank Professor Tavansky of the University of Iowa, along with his graduate students, for generously allowing me to use the images I used in the AFM from their lab. Thank you so much for listening to my presentation.